So the t-distribution is a distribution that is similar to the normal distribution, except it has the property that the information is not as concentrated around the mean. So for example, if I think about the normal distribution being a distribution that looks more or less like this, the t-distribution is going to be a distribution that looks maybe a little bit more like that. Okay, so the information is not as concentrated around the mean as in a normal distribution. So this would be a normal distribution, and this would be a t-distribution. Now, a t-distribution is obtained from x bar minus mu divided by the standard deviation over square root of n. And the idea there is that because you're considering at the denominator the sample standard deviation and not the population standard deviation, then you're introducing variability into your random variable, not only from the variability of the mean, x bar, but from the variability of the standard deviation as well. Right? You have two aspects that are introducing variability to your random variable, which means that we should expect this to be a little bit more variable because we have two sources of uncertainty, right? This is why we have a more spread out distribution. Now, how spread out the distribution should be depends on how much variability I expect there to be, right? So it depends on how inexact I expect S, the sample standard deviation, to be. Now, that fact that we have a distribution that involves these two sources of variability makes it so that it's less variable, and that variability is going to depend on how uncertain my standard deviation is, which means that it depends on how large my sample is, right? Because if I have a sample that is larger, that means that my standard deviation estimator here, S, should be closer to sigma, right? And so the larger my sample is, the more information I have about my population, and the closer the t-distribution should get to the normal distribution, okay? Because the least variability I should expect from that sample standard deviation, okay? Now, that means that the t-distribution is going to depend on the sample size. It's going to depend on the sample size. And the larger the sample size is, the closer this is going to get to the normal distribution. Okay, so for example, if I had a slightly larger sample, this would look maybe like this. And if I had an even larger sample, it would look maybe like that. And I can keep going like that. And as the sample size goes to infinity, the t-distribution approaches a normal distribution. Okay. Once again, that's because the smaller the sample is, the more variability I should expect from sigma, so the more variable my estimator should be. Whereas if I have more and more information, then I'm tending toward a sample that has a lot of observations, and therefore the central limit theorem will end up applying. Could I please see a yes for everybody that understands this? Okay. So the distribution, the t-distribution, once again, we're not going to really look at the density function. We're not going to evaluate integrals in order to evaluate probabilities. We're going to use a table that is similar to the normal distributions table, except it's used for a t-distribution. And it looks slightly different from the distribution, from the table that we had for the normal distribution. So in the normal distribution, we have a table. On the boundaries, we have the edges, right? And then inside we have the probabilities. for this distribution is going to look a little bit different. So the first thing that we have is, so here we have a student T percentage point. What we have is that, where's my highlighter? There you go. We're going to include a parameter here, a thing that is called degrees of freedom. Okay, the degrees of freedom tells us which T distribution we should be looking at specifically. Is it this one, or is it this one, or is it this one, right? And that's going to depend on how large my sample is. Okay, so the degrees of freedom are going to be dependent on the sample size. They're not going to be equal to the sample size, so I don't want you to ask to write that down yet, but they're going to be dependent on the sample size. And then instead of having the percentages inside the table and looking for the corresponding values outside, what you have is that these are the percentages and these are the boundary points. Okay, so I'll highlight, I'll color code everything. Hopefully that will help you a little bit. So here, everything that's inside the table corresponds to the boundaries. Okay, so all of this. And then you have that this part here corresponds to the percentages. Okay, so I'll do a little sketch of what this corresponds to. So I have first that the T distribution is going to look similar to a normal distribution. I'm going to create two similar ones. Yeah, so the number of degrees of freedom tells me whether I'm considering one of the distributions that is a little bit wider or one of the ones that are almost identical to a normal distribution. Okay, so it tells me which of these distributions I'm going to look at, or anything in between, right? Once again, the larger the number of degrees of freedom is, which corresponds to the larger the sample is, the closer I'm going to get to a normal distribution. Then the orange part over here is going to tell you the percentage, which means it's going to tell you the area under the curve, or the area under the curve here. And the filling of the table, okay, or the purple side here, that's the part that corresponds to the edge. Okay, so it's a little bit different than the Z table, where inside the table you read the percentages and on the outside you read the edges. In here, it happens the opposite way. You have the percentages at the top bar, and at the bottom you have the edges. Now, what happens here is that because the T distribution is only, at least in the context of this class, is only used for confidence intervals, or for the next part that we're going to see, which is called hypothesis testing, then we don't need as many values for the probabilities inside, which explains why we have limited probabilities that we're interested in. Okay. So we have limited probabilities that we're interested in, that's fine. And then, for example, if we wanted to find the value that separates the bottom 95% from the top 5%, and we had 3 degrees of freedom, we would have to go to this row over here. Okay, but I'll let you think about that once you're trying to solve a problem. Yeah, so that's over here. That's the distribution that you're going to use. Now, for this type of distribution, you're going to have that the number of degrees of freedom is going to be n minus 1. So it's whatever your sample is minus 1. Okay, and aside from that, you're going to use everything else in exactly the same way as for a normal distribution, because it turns out that this distribution is also symmetric. And so you can use all the same logic that you've used for the normal distribution here as well. Okay. All right. And then you have the other two types of confidence intervals, one of which works for large samples that come from unknown distributions. Oh, yes, Lori.
Should we print this table as the other one?
Yes, so you can print it. It's already available on Leia. So you can use it, either on your computer, or if you like paper versions, then you can print the paper version for it. It is not the last table we will see in this class. We'll have another table, I think, one more. So yeah, and so then the third one over here applies for a population of unknown distribution when you have a large sample. It's going to be very similar to the one that you have here, except here you have the standard deviation for the sample. And in the last case, you have a confidence interval for a proportion, which is going to depend on the sample proportion only. All right, so what I would like you to do is then try to work on the problems that I'm going to put on the board. I'll give you a little bit of time to write those problems, and then I'm going to, so while you write the problems, I'll be making the groups, and then I'll ask you to join the groups. All right? Okay, so here we go. I have 4 problems to write, and in each of them you're going to have to create a 90% confidence interval for the parameter that is of interest in that problem. Okay, so it's a general case so that you just have little guidance and you have to kind of figure it out. That's the point of these ones. The first thing is that in the first example, you had a sample of 17 teenagers that were surveyed about sleeping patterns. And the responses suggest that they slept an average of 8.07 hours per night with a standard deviation of 0.56 hours per night. We're going to assume that sleep time is normally distributed, which is an important, it's a thing that you need to pay attention to. All right, so the parameter that we're interested in this case, is going to be mu, which is the average sleep time or mean sleep time for teenagers. Okay. Then you have that the sample size in this case was 17. You have that the average for the sample was 8.07. And you had that the standard deviation was 0.56. And this was for the sample, right? So the standard deviation here is reported along with the sample average, which means that both the average and the standard deviation are computed for the sample. Now, what this means is that we have, so this is plus, it's normally distributed. Now, what's normally distributed is the sleep times across all the teenagers. But because we have a small sample, we can't assume that the distribution here is going to have a normal distribution, especially because we don't have the population standard deviation. In this case, we only have the sample standard deviation. And for this reason, we're going to use the second formula in our table. Let me go back to what we have here. We have a normally distributed population, that's a check, and then we have that the population standard deviation is unknown because we are only given the sample standard deviation. This means that I'm going to have to use this formula in order to evaluate the confidence interval here, right? So what that means for us is we're going to have to find an interval of the form x bar plus or minus t, where the degrees of freedom are 17 minus 1, so n minus 1, and alpha is alpha over 2 is 0.05, right? Because we're looking for a 90% confidence interval, and then this is times s over square root of n.
Miss.
Yeah.
So, like, why do you say the sample, like, the deviation is unknown? Like.
No, I'm saying the population standard deviation is unknown. So what's known here is the sample standard deviation and not the population standard deviation.
Okay.
Okay. So because of that, we're going to use this formula. Now, what that gives us is x bar, which is 8.07 plus or minus T17 minus 1, 0.05. I'll talk about that in a second. And then S is 0.56 divided by square root of N, which is square root of 17. I don't think I'm going to have enough space, so it's fine. Okay. So if this is the case, I'm going to try to find T17 minus 1, 0.05, which means the value that separates the top 5% from the bottom 95%, and such that the number of degrees of freedom here is 16. Okay, so that means I'm trying to look for, I'll do the drawing here, the distribution, the value that separates the top 5% from the bottom 95%, right? Because I'm trying to find a 90% confidence interval, which means I need to chop 5% from the top, 5% from the bottom. At this point, I'm going to have, this is going to be the value that I'm looking for. And I know that my number of degrees of freedom here is 17 minus 1, which is 16. If I look in my table here, that means that I'm looking for the value that separates the top 95%, at the top 5% from the bottom 95%. So I'm going to be looking in this column. I'm going to be looking in this row for the number of degrees of freedom. And that means that the value I have is 1.746. I would like to see a yes or no for whether you found this value. All right. I would like to know what the mistakes were.
I just used the wrong formula. Like we didn't use the T thing. We used the first one.
All right.
It's normally distributed, and we know the standard Oh wait, never mind.
There you go. All right. Okay. So people that used the first formula instead, was there? Okay. So I'm going to clear everything. Was there anybody that used the right formula but didn't find the right value for T? Okay, so that means the problem was not finding the value, it was finding the formula. That's perfectly fine as well. Happens. Okay, so now you know, if you don't have the standard deviation for the whole population, you can't use that first formula. All right, and so in this case, we had 1.746, which means that the interval here, if I didn't make any mistakes, is going to be 7.83 to 8.31. All right. Yes, Laurie.
There's not a big difference between these values and the ones we found before.
Yeah, there aren't big differences, but, and that's because the sample size here is not absurdly small. So the smaller the sample size is, the further away your interval is going to get. Now, also, you know, we're in a class, we're just doing a little bit of practice. So a little bit of difference is not that important. But if you're trying to think about, I don't know, like scientific scenarios in which you need a lot of precision, then that difference might make a difference. Okay, so. All right, I saw, okay, same mistake, that's good. Now, I would like to see someone interpret this interval. Okay, so if you're willing to speak out loud, I would rather somebody speak out loud. I would like to see how you interpret this interval, 7.83 to 8.31. You can raise your hand if you're willing to speak up on the mic. No one volunteering as tribute, really. There you go, Sarah, go.
Well, I just said, like, I'm not sure if we're supposed to use the personal pronouns, but anyways, I said I'm 90% confident that the interval 7.38 to 8.31 contains the true mean of the teen's sleep pattern.
That's perfectly right. Yeah. So you're 90% confident that the true mean is in this interval. Again, the thing that you need to avoid is to try to say that there's a probability that the mean is in this interval. That's not the case. There's nothing random about that mean, or that 90% of the means are between these values. That's also not the case. So it's really important to refer to that level of uncertainty as a level of confidence. Okay, so you have basically here we're 90% confident that the mean sleep time for teenagers is between these two values, okay? Which again is the same as to say, if I were to, I'll answer your question in a second, Serena. So you can either write it on the chat, or if you're willing to say it out loud, then you can wait for 2 seconds. So this is the same as if you were to say, if I take 200 identical samples, I should expect 90% of them to contain the true mean. Therefore, I am 90% confident that mine does. Okay, so it's really a matter of how confident you are that you are in one of those positive scenarios in which you did indeed capture the mean. Yes, Serena.
So my question is, let's say that the question was to interpret a 95% confidence interval. Then how would we do it differently?
The one thing that would change is, first, in terms of the interpretation, you would simply have to change this value here. And the only value that would change in your formula would be the t value here, right? Because instead of the 0.05, instead of chopping 5% from the top of the distribution, you would be chopping 2.5% from the top of the distribution. In that case, you would have to go to your table, and instead of looking at the column for 95%, you would look at the column for 97.5%.
Okay, thank you.
All right, Rita.
In real life scenarios, like how do they determine the percentage of confidence?
It's arbitrary, which is yeah, kind of unsatisfying. There's conventions depending on the field that you're in. So for example, in psychology, there's often that like 95% is the usual confidence level that is required. But if you were to do something like, I don't know, medicine, then you would have to have a higher degree of confidence. So you would have, let's say 99.9%, and so on. But it's arbitrary. Which is why every time that we are doing something in class, I will ask you specifically what I want. And Vishaka.
So yeah, you said that like the average they give was for the sample, but let's say like if it was for the population, it would be specified like the average of the population.
Yes, or I would say, so not the average, the standard deviation. So if I were to specify it for the population, I would say something like, it is known that the like in this case, sleep times are normally distributed with standard deviation blah, and then I would give you the average for the sample. You can think of that, for example, D, where you have that. First, I talk about the distribution. I say the SATs are normally distributed with a standard deviation of 150, which means you know the standard deviation for the population. And then I talk about the sample and the results that you got from there.
Okay, so then like in this case, like the standard deviation wouldn't change for like the sample. Right.
I'm not sure what you mean.
Like in the formula, we would use 150.
Yes, exactly. So for D, essentially the thing that changes is that standard deviation that you're given is sigma and not S. And because it's sigma, you can use the first formula instead of the second formula because you do know the population standard deviation.
Okay. Okay.
Right. I'll give a quick solution for B. So in B, we have that in a sample of 200 freshmen, 80 report that they work 20 hours or more while at school. So the parameter is P, which is the proportion of freshmen who work 20 hours or more while at school. Okay, so it's that proportion. The sample size here is 200. The sample proportion is 80 out of the 200, right? So if I were to estimate the proportion of freshmen that work more than 20 hours while they are at school would be 80 over 200, which is 40% or 0.40. And then you have that n times that proportion is 200 times this, which of course is 80, and n times 1 minus this is 120, both of which are larger than or equal to 5. Okay, which is something that we need to check in order to use the normal distribution. So from here, I can use the formula given in the last row here, which tells me that the confidence interval for this is going to be p hat plus or minus z alpha over 2 times the square root of p hat times 1 minus p hat divided by n. Okay, and from here we get that this is equal to 0.40 plus or minus the square root of 0.40 times 0.60 divided by 200. And Z alpha over 2 here, we're going to find in our table, it's the value that separates the top 5% from the bottom 95%, which hopefully you found to be equal to 1.645. Okay, now one of the last things I'm going to ask you to do today, who found this? Could I please see a yes for everybody that found this value for Z alpha over 2 and a no for everybody that did not? All right, if you did not find this value, I would like you to write on the chat, what was your mistake? Maybe we don't know what the mistake was. Oh, we used the wrong distribution. Okay, so good rule of thumb is if you can estimate something for the proportion, it's always going to be the normal distribution. Okay, the t-distribution is only used for the mean. Okay, so that's a good way of remembering. So that's okay. So as long as you're able to find it from the Z distribution, I'm good with this. Again, all that we had to do in this case was find the value that corresponded to 95% in our table and then look at the corresponding margins, which was 1.6 and then exactly in between 4 and 5. So it would have been 1.645. Okay. And from here, you would have gotten the interval 0.34 to 0.46. Okay, so this is your 90% confidence interval. Once again, if you were to interpret it, you would have that you're 90% confident that the proportion of freshmen who work over 20 hours a week while they're at school is between 34% and 46%. Okay. I'll just give the answers for C and D. So in C, you have to use the third formula. Yeah. So in C, you have to use the third formula. And the justification is that 120 is larger than 30. Whereas in the last case, you have to use the first formula. And the reason is that you have the standard deviation for the original population. Okay, Rita, you have a question.
Yeah, in the previous example, why is it 200 and not divided by 80?
Because 80 is the number that have the property and 200 is the total size of your sample.
Okay.
Okay. So then you have that here you have to use the third one. Here you have to use the first one. The reason here is that there's 120 workers, which is larger than 30. And the reason here is that you have to use, is that you have the standard deviation for the whole population. Vishaka, for your question, when to use each distribution, you should always be looking at the conditions. Okay, this is what that column is for. So the conditions here tell you exactly when you should be using each of the distributions that you're given. Okay, so that's the direction that you have to go. And Lori.
In an exam, are we going to get these conditions?
Probably not, but we're going to be working with them a lot in the next couple of weeks, so you'll know how to use each of them.
But we do have the rest of the table.
You have the rest of the information, yeah.
Interesting, okay.
All right, so at the beginning of next class, I'll give the final answer to both of these. I would like you to try to do them by Friday. And you also have the practice set homework 8, I believe, which is not due anytime. You don't have to submit your answers, but which I strongly suggest you start practicing with, because as you can realize, the challenge in all of these problems is to try to identify what you need to do. Once you know what you need to do, it's really easy to do it, but you have to know what you are trying to do. So that's that for today. On Friday, we're starting something new. I will take a couple of questions at the beginning, but then we'll start to do something that's called hypothesis testing, which is kind of the highlight of statistics. It's everything that we've been working toward. And that's that.